So we're in chapter 4, last lecture on first law analysis for open systems. We're really going to touch on transient analysis for open systems today. This is really the only real part of a transient analysis in the whole textbook, believe it or not. You can go digging. Everything else is based on steady state operation of the compressor, steady state operation of the pump, steady state operation of the heat exchanger. Okay? So when you do a transient analysis, just write the control volume analysis for conservation of mass and conservation of energy clearly. That's it. And follow the terms. I think it's easiest to solve a problem because you have the equations. There's no new equations to derive. So let's solve this problem. We have a 1,250 liter tank containing steam, and the pressure and temperature are given, 30 bar and 320 degrees C. If you do have your appendices, I'll go look at some numbers today. A valve is opened and steam flows out of the tank at a constant flow rate of 0.009 kilograms per second. So maybe you'd start doodling. You say, oh, I have a tank. I have initial temperature and initial pressure. I have a valve or some leak is opened or it's partially open, and I have some flow rate out, mass flow rate exiting of 0.009 kilograms per second. During the steam removal, a heater maintains the temperature within the tank at 320. So let's think about this heater. And you can view it as dumping heat, Q dot, into the contents of the tank. The heater, I know it has electric power, but that's all converted 100% into heat transfer, and so let's just model as Q dot. And it's able to maintain the temperature such that the temperature stays at 320, even though some of the steam is leaving. So it's like the final, you think about the initial temperature T1, the final temperature T2, the initial pressure P1, the final pressure P2. The valve closes when 35% of the initial mass of the steam leaves. So if 35% has left, how much remains? 65% of the mass remains in the tank that was originally there. What do you think the pressure does? The pressure stay the same? Go up, go down? Temperature stays the same. Is this volume of the tank changed? No. Let's organize some information. Let's talk about state 1 and the state 1 things that don't change are the volume of the tank. So V1 of 1.25 meter cubed is equal to V2. Volume of the tank doesn't change from initial to final state. The temperature of the contents start at 320 degrees C. Because of the heater, they stay at 320 degrees C. The pressure starts at 30 bar. We don't know what the final, that's P1, not P2. We don't know what the final pressure is. It was just my question I asked. Did it go up? Did it go down? Did it stay the same? Some of the mass escaped. Let's take, do you think we can get V1, the specific volume, U1, and H1 properties for the steam that's in the tank at state 1? Sure, we can go ahead and get that. It would be 0.0850 meter cube per kilogram from the table. U1 is 2788.4 kilojoules per kilogram for internal energy, and enthalpy is 3043.4 kilojoules per kilogram. Okay. They ask us a few questions, A, B, C, D. We can, from the tables, we get these properties. Now we're well situated to answer the question A. What is the initial mass of the steam in the tank? So what is the M1, the initial mass of the steam in the tank? Is it the initial volume divided by the initial specific volume? And when you substitute numbers, M1 comes in at 14.71 kilogram. Part A is done. What is the specific volume of the steam in the tank when the valve closes after 35% has left? Well, what we do is we say, what was the mass that remains? Well, it's 0.65 of the mass that began. And so the mass that remains is equal to 9.559 kilograms. Hence, we can come up here and maybe put V2 just so it parallels where the location is. So V2 is volume per unit mass, volume 2 divided by M2. We now know the mass that remains in the tank. There's a specific volume of the fluid that remains in the tank. Is it greater, less, equal to the specific volume of the steam that was initially in the tank? That's right. So it's 0.13077 meter cube per kilogram. What were the two independent intensive properties that helped us fix state 1? Temperature, pressure, from which we were able to get the VUH. Now we have state 2. What are the two independent intensive properties that fix state 2? V2, T2. You could use those two properties in your tables and get P2. Somebody want to tell me what P2 is? I should have boxed my second answer. My second answer was it's right at 20 bar. The pressure went down. So I should have boxed it, but V2 is 0.1308 meters cubed per kilogram, good to 4 significant digits, and that number is precisely in the table at 20 bar. Yes, I worked a long time to pick these numbers. So you avoided the interpolation. Otherwise, we have nasty interpolation. But in general, we could have said, let's say if it wasn't 35%, let's say it was 25% of the initial mass leaves the tank. What do you think the pressure is going to be? As low as 20 bar? Lower than 20 bar? Or between 20 and 30 bar? It'll be higher. It'll be higher. You would have had some nasty interpolation. Or I shouldn't say nasty. It's just extra work, isn't it? That's all it is, just extra work. So that's the answer for part B. What's the pressure in the tank? 20 bar, that's the answer for part C. What is the time that the valve is open? How long is that valve left open? Well, we know that the mass flow rate exiting is that much. You know, we know that rate at which it exits. So let me do this. Let me go ahead and draw a nice little control volume. We'll include the valve. The valve really doesn't contain any mass, but we'll include the valve. And now what we do is we say, okay, let's do a mass balance for that control volume. The time rate of change of the mass inside the control volume is equal to the rate at which it's coming in, adding to its mass, minus the rate at which it's flowing out. True? Of those three terms, which term is 0? M dot I, M dot N. True? So the mass flow rate in is 0. All we have is outflow. Could I take and separate and integrate, and we would get that the mass in the control volume at the ending state, at the final state, minus the mass in the control volume at the initial state is equal to the minus the integral of the rate of change, the rate at which it's exiting, dt. Good. Good, good. You like that math? And so because the rate at which it's exiting is a constant, what can we do? Take it outside the integral. Makes it so easy. And so what we have is we have minus the rate at which it exits times the time. And that's what we're interested in for part D. What is the time that the valve is open, and when it's open, some flow is leaving? So the amount of time that it's left open is the mass in the control volume final state minus the mass in the control volume initial state divided by the mass exiting. And if you want, you put a minus sign there or switch the order in the numerator of this quotient. Okay, and we calculate that the time it's open comes in at 572 seconds. So it's open for about 9.5 minutes. All right. Next part is what is the heat transferred during the process? We used a mass balance to solve for part D. What type of balance do you think we use for E? Energy balance. So let's write down the energy balance. Would it be something like the rate of change of energy in the control volume with respect to time is equal to the rate at which it's flowing in with heat minus the shaft power out plus it flows in with its enthalpy in, specific kinetic energy in, potential energy in, minus the rate it flows out. This is an inflow. This is an outflow of its enthalpy exit, kinetic energy exit, potential energy exit. I know I barely fit it in. Doesn't look so clean, does it, at the end? Kind of scribbled a little bit. Sorry about that. Okay, which term is zero? Is it steady state? Is the rate of change of energy in the control volume zero? No, that's a transient analysis. So don't strike this term. Q dot's not zero, but this term for the shaft power is zero. Do we have any mass flow rate in? No, so all of this just goes. Right? And now there's no information about kinetic potential energy, and so you assume that that part of the exiting stream is negligible. I don't have any information to calculate it. And so it's simply taking with it its enthalpy, exiting enthalpy. So we want to separate and integrate this. So we get that the energy in the control volume at the final state minus the energy in the control volume initial state is equal to the integral of Q dot dt plus minus the integral of the enthalpy exiting mass flow rate of the fluid exiting dt. Does that look okay? You see what I did? All right. So I have to scoot down. I'm really sorry, but I'll scoot down just a little bit to get me some room here. This is the term we're asked to solve for, isn't it? Isn't that the heat transfer during the process? It's not. It's the rate over the time, integrated. So that ends up the amount of heat transferred during the process. Okay, so I can put it like this. The integral of Q dot dt is the Q 1 to 2. It's the amount of heat transferred during the process from initial state 1 to final state 2. Okay, and that's equal to the energy control volume at state 2 minus energy control volume state 1 plus the integral of the exiting enthalpy of the steam mass flow rate dt. We look at this equation very longingly and we say, you know what, if this could be a constant, it would come outside the integral, true? If the enthalpy of the flowing steam that's leaving that control volume is constant during the time period it's leaving, I can bring that outside the control volume. If that's true, then you're just going to get the enthalpy, the exit, times the mass that left, isn't it? Which would be the final, well, initial mass minus the final mass. Wouldn't that be the amount that left? We started with a bunch, we ended with a little, some of it left, that's how much left. Okay. Notice that I moved this to the other side, hence that negative sign turned into a plus sign. True? So it's easy to make a sign error, but let's see. I'm trying to calculate the amount of heat transferred in the process from initial state to final state, Q1 to 2. Now I need to work on what is the energy in the control volume at the final state. What is an equation for that, for this term? And then what's an equation for that term? Well, how is energy stored? In the form of internal kinetic and potential energy. We only have information about the internal energy, so we neglect kinetic and potential energy. I mean, to have some kinetic energy, it would either have to be moving or rotating as a whole system. There's nothing about, its rotational rate or its velocity, overall velocity. The whole tank is moving for some crazy reason. So this just gets to be the mass in the control volume final state times U2. What do you mean by U2? The specific internal energy at state 2. Then we have minus the mass control volume 1 times U1. Let me ask this question. Are these the same? Yeah. That's the mass that's in the tank at state 2 at the end of the process, and the mass in the tank at state 1 at the beginning of the process, which we calculated. Here is the mass in the control volume at state 2, 9.559 kilograms, and the mass at state 1, 14.71 kilograms. Okay, I have to scroll down a little bit more. Hate to do that. But you come down here, you go back to the table, you get U2, just like we got U1. When we get U2, it's 2807.9 kilojoules per kilogram, true? And let's get H2. H2 is 3069.5 kilojoules per kilogram. Now, this exiting is, initially when it starts to exit, it's coming out, the enthalpy of the exiting fluid's coming out at 3043.4. At the very end, near the end of the transient, it's exiting, the enthalpy's coming out at 3069.5. As a mechanical engineer, what's the difference between those two numbers? Very small. So guess what we're going to do? We're going to put the AVG right there. And what do you think we're going to put for the enthalpy of the steam that exits as an average value during the process? It's initial, it's final, divided by 2. We have to do something to make the problem solvable. Looks like a reasonable assumption to me. Somebody else said, hey, less than 1%. So that average value comes in at 3056.5 kilojoules per kilogram. When you read this chapter, and when you find that you have to do this integral of some property with respect to the mass that's leaving, you often need that average to be able to compute this integral. Otherwise, you have to resort to computer code or something to do the calculation. But this is very justifiable for this case. All right, so let's now stick in our numbers. We have the final mass in the control volume, 9.559, times the internal energy at state 2, 2807.9, minus the initial mass in the control volume, 14.71 kilograms. The initial internal energy, 2788.4, plus the average enthalpy, 2056.2, times how much mass left the control volume. I think I already calculated that somewhere. But I don't know where I see it on my sheet. But 5.1471 kilograms left during the process. And so the Q, 1 to 2, comes in at 1566 or 1570 kilojoules. This is a 3, isn't it? So I messed up the 3. 3056 point. What is that? Is that a 2? Where was I looking for these numbers? Wow. So about 1570 kilojoules.
When you do the change in mass, why don't you do final minus initial rather than
All right. Yeah. Let me see if I can come back up here. Yeah. Okay. This. I'm going to try and squeeze it in right here. This equation we agree with, the one I underlined, true? And so then if I wanted to put a plus the integral m dot x at dt, it's the mass and the control volume initial minus the mass and control volume final, just from here. Make sense? Yeah. Any other questions? How does it feel to solve transient problems? Not that bad, huh? Yes, sir.
Is this kind of problem solving something that we'll be doing in exams from here on out?
No.
Where we make simplifying assumptions
Yes.
and we interpret things as being zero. So one of the things I keep getting stuck on with these problems is that in the past, if I wasn't allowed to assume it by the problem, I'd get marked wrong if I assumed it. But now it seems like we're encouraged to make assumptions.
Yeah, I know. When you studied chemistry, you had to balance your equations. You had to use whole numbers or fractions. Guess what? Engineering, if you want to put a 3.179 down, go for it as a stoichiometric coefficient. And the chemist would slap your hand. Say, don't do that. Right? But tough. We can do that. In engineering, half of the game is figuring out what's important. And so maybe this is one of those transitional courses where it's like, okay, we've got the mathematical tools, we have some engineering principles, conservation of energy, conservation of mass. We could solve a lot of problems, but a lot of these problems, sometimes the kinetic energy, potential energy is negligible. And then sometimes it's not, and you have to decide when. So, but we're not going to solve a whole lot of these type of problems, which mean transient problems. Just this section of the textbook, true transient problem. A rigid, well-insulated tank, 0.5 meter cube volume is initially evacuated. How much mass is an initially evacuated tank? Zero. What's the pressure in initially evacuated tank? 0. The temperature is not 0, it's just not defined. Okay? I mean, it's like, what's the temperature where there's nothing in mass? Well, that's just, let's not talk about it. To me, it's not definable. You have to have something that has some molecular kinetic energy or molecular vibrational energies to detect its temperature. All right. So we have this tank. It's well insulated. It's rigid, and it's initially empty. Air from the surroundings at 1 bar, 27 degrees C begins to flow in the tank. At the same time, an electric resistor transfers energy to the air in the tank at a constant rate for 30 seconds. After which time the pressure in the tank is half a bar, and the temperature of the air is 167 degrees C. Air behaves as an ideal gas. Determine the power input to the tank. So what's that? What are the watts of that resistor that's transferring that energy into the tank, into the air in the tank? So we make a sketch. We have a tank. Maybe I put it over here. There's a little hole or restriction. It goes into the tank, and we have a heater that heats up the air in the tank. Okay. I'm going to say that the air comes in at 300 Kelvin, that's 27 degrees C, and 1 bar. And the volume of the tank isn't changing, 0.5 meter cubed. And maybe I introduce a control volume. I put it there because I know what's coming in. I know the temperature, what comes in, the air, and the pressure at which it comes in. I think about 1, the initial state, it's evacuated. And the mass in the... sometimes I'll put MCV1 or just M1. You know, it's the mass in the control volume, it's the initial state 1. Okay, 0 kilograms. The temperature 1, not defined, you know, it's not applicable. And the pressure 1 is 0. It's no pressure. Okay. And then state 2, this is after 30 seconds. It has some mass in the tank. Didn't tell me. They told me the temperature 2, 167, which is 440 Kelvin. And the pressure 2 is a half a bar. Okay. So I try to organize my information. Initial state, final state, it's evacuated, it has some mass in it, etc. And then I say, what is the power input to the tank? So what we're trying to calculate is, maybe we're asked to calculate Q dot in units of watts. Would that be the power input to the tank, Q dot, in watts? So our symbol in units. Okay. So we're going to do a mass balance. If you do a mass balance for that control volume, we get that the rate of change of mass in the control volume with respect to time is equal to the rate at which it flows in minus the rate at which it exits. Now, is there any exiting? So it's just a positive inflow. So we separate, integrate, we get the mass. That's the final amount in the control volume minus the mass, that's the initial amount in the control volume, equal to the rate at which it flows in dt. Seems like a trivial statement, but there it is. This one is 0 because it's initially empty. Is there any way that I could calculate the mass that's in the control volume at the end? Is there any way to calculate? Ideal gas equation, true? So is M2 equal to P2, volume of the tank, molar mass of dry air, ideal gas constant, the gas constant, divided by T2? Is that a good equation for the ideal gas equation to get the mass in the tank? And I think we've done this enough. You stick in the numbers and you can calculate the mass in the tank is 0.19798 kilograms. About 0.2 kilograms. That's how much air is in the tank at the final state. So basically we know or have calculated how much comes in. 0.2 kilograms, 0.197, blah, blah, blah. Okay. Well, let's do the energy balance. All right, so the rate of change of energy in the control volume with respect to time is equal to the rate at which it's flowing in with heat minus out with shaft work. And we're going to say it comes in, bringing with it its enthalpy. I'm neglecting kinetic potential energy coming in, minus mass flow rate exiting, taking away its enthalpy. Well, there's nothing exiting, no shaft work. So we separate and integrate. We get that the energy in the control volume at state 2, the final state, energy control volume state 1 equal to the integral of Q dot dt. plus the integral of the enthalpy in mass flow rate of mass coming in dt. Well, why is the energy that's in the control volume initial equal to 0? It's evacuated. And so this term is what we're trying to solve for. So that becomes Q1 to 2. That's, I shouldn't write it like that, should I? I look at the problem and it says, at the same time, electric resistor transfers energy to the air in the tank at a constant rate. So can the Q dot come outside the integral? Constant rate. So basically this is the rate at which the heater is transferring energy inside times the time at which it's run, 30 seconds. It's run for 30 seconds. And we're looking to solve for Q dot in units of watts. And there it is. True? Okay. So what is the energy control volume final state? That's the mass in a control volume final state times its internal energy final state. And then we're going to come over here. What do you think we do here? Is the enthalpy of the air that's coming into the control volume changing? Or is it always 300 Kelvin air at 1 bar coming in? It's always 300 coming in. So this is just the mass. Here, this is the integral m dot dt times enthalpy in. True? And guess what the integral m dot dt is? m2. So this is simply the final mass in the control volume. So we can solve for Q dot. Q dot's equal to the final mass in the control volume, internal energy at the end, minus the enthalpy of the inflowing divided by delta T, the time that the heater's on. This is a little funny because on the internal energy right here, I need to get U2. So I have a number for the subscript on that property. So the internal energy of 440 degree Kelvin air, I can just get that out of a table, is 315.30 kilojoules per kilogram. Likewise, the enthalpy of incoming air at 300 Kelvin out of the same table comes in at 300.19 kilojoules per kilogram. So the subscript I for incoming and the subscript 2 for the final amount in the tank. Be careful with our subscripts, right? So we calculate that the rate at which it comes in is 99.7 watts. Okay, any other questions? I'm going to press forward then. So basically we've covered it. We've covered the chapter. You need to be able to analyze nozzles, diffusers, turbines, compressors, pumps, heat exchangers, and throttling devices. And there's multiple types of heat exchangers. There's multiple things like a gas, refrigerant compressor, air compressor, the types of compressors. Turbines, you could have a hydraulic turbine, a steam turbine, a gas turbine. So there's just a lot of applications. And the way to get good is to practice and solve a lot of problems. One of the things I encourage you to do is to go through this table. Did I not last time at the end of the last lecture? So you could just pick one of these. Let's say, so let's take a look at a steam turbine. So here is the typical schematic. It comes in, it goes out, and what's so special about this little line right here? It's a shaft. And so we have W dot out of the control volume that surrounds this steam turbine. For a steam turbine, is there any heat transfer with the surroundings? That's our standard assumption. They may give you a problem where they say, and oh, by the way, Q dot is so many kilowatts. Well, then you have to embed that into the first law. But most of the time, Q dot, it's well-insulated turbine, it's 0. This is the positive shaft work out. That's the purpose, is to develop shaft work. That's the purpose of that steam turbine. What about the pressure change? This is P2 minus P1. What about the exit pressure compared to the inlet pressure? Lower. This could be negative. The exit pressure is less. What about the exit temperature, T2 minus T1? It's negative. It's lower. It's less. How about the speed, V2 minus V1? Often that's negligible. Otherwise, they have to tell you, oh, this is the inlet diameter, that's the outlet diameter, mass flow rate is constant, hence you know you can calculate V1 and V2. And if you did and it was a real problem, you'd probably find that it's coming out a little faster because it expanded. Okay? But most of the time, it's 0. What about the change in kinetic energy? If the change in speed is 0, that's often is 0. And what about the change in enthalpy? Exit enthalpy minus the inlet enthalpy. That's what made the shaft turn. We converted fluid power into mechanical power. So this is negative, isn't it? The exit enthalpy is a lot lower than the inlet enthalpy. All right, so that was the steam turbine. Somebody else pick another one. Pump. Okay, let's take a look at a pump. Often you draw a little guy like this and they come in like that, and it comes in at pressure 1 and goes out at pressure 2, and you have a little control volume around it. Now, I'm going to stay with the traditional sign convention that Q dot in is positive and W dot out is positive. True? But we know that a pump has a shaft providing shaft power into the pump to make it work. So, what about the standard assumption for Q dot for the pump? 0. What is W dot into or out of the pump? It's going to be negative because it's truly into the pump. What about the change in the pressure? How's P2 compared to P1, the exit pressure? It's positive. That's the purpose of the pump. How about the change in the temperature, T2 minus T1? Itty bitty, and I mean itty bitty increase. Like 0.2 degrees C, 0.3 degrees C, something like that. Even though you have a huge boost in pressure. So guess what the standard assumption is? 0. No real change in temperature. The purpose of the pump is not to make the water increase in temperature. The purpose of the pump is to boost the pressure. Real systems, yes, there will be a slight increase in temperature. There will be a slight increase in temperature. Even for an isentropic pump, a perfect pump. Okay, it's not just a frictional beating it up. A great pump will still increase the temperature ever so slightly. All right. What about the change in the speed? 0. Purpose is not to speed it up. It's to boost its pressure. How about change in kinetic energy? 0, same thing. How about the change in enthalpy? Goes up. So it's positive. And now you have H2 minus H1. Now, somebody says, why does that go up? Well, come down here. It's H2 minus H1. Is that U2 minus U1 plus P2V2 minus P1V1? And if I have liquid water, it's incompressible. We just talked about a negligible change in temperature. And then if it's incompressible, these are the same. And so the change in enthalpy for a pump is V times P2 minus P1. Great. I know it's not good to 18 significant digits because There is a slight increase in temperature, so this is approximate right here. Although it's a great approximation. But this is also approximate, and it's a great approximation. VDP, specific volume times the change in pressure, is the increase in the enthalpy across that pump. Make sense? So if you know the pressure increase, what's the specific volume of liquid water? 0.001 meter cubed per kilogram, roughly. Right? Okay. Do we want to pick another one? Which one? Hydraulic turbine? Okay, it's going to be very similar to a pump because a pump is like a hydraulic turbine in reverse, isn't it? So let's do a hydraulic turbine. Q dot, 0. W dot, positive. See, we want some positive work out. This is like positive as well. Delta P. It goes down. What about the change in temperature? Negligible. Change in speed. Really, you don't want to... I know that it goes fast in the interior of the pump, but then when it finally comes out the exit pipe's about the same diameter as the inlet pipe, and it's incompressible, about the same. And negligible change in kinetic energy. What really drives it is the change in the pressure, which is, so it's a negative change in the enthalpy. And when you look at the enthalpy change across a hydraulic turbine, the liquid water turbine, like in a dam, it really is that pressure difference from inlet to outlet that drives it. Okay. How about another one? Throttling device. What symbol do we use for throttling device? Something like that. Comes in at state 1, goes out at state 2. Now, you can throttle air, an ideal gas. You can throttle refrigerants. We don't really throttle a whole lot in applications of air, an ideal gas. We throttle refrigerants. So we want to really understand why, if we put a refrigerant in here, and we have a high pressure and a low pressure, what happens? So, whoops, I got to go back, look at my headers. So Q dot for a throttling device. It's not a heat exchanger device with the surroundings. W dot. There's no shaft work in or out. Change in pressure. It goes down. There's a large negative decrease in pressure. Okay. What about the change in temperature for a refrigerant? It goes down a lot. Goes down a lot. So it goes down, decrease. It's negative. Okay, how about the change in the speed? Really, the change in the speed and the change in kinetic energy up here in the nozzle diffuser. It's kind of boring for the rest of the table, 0, 0. All right? The nozzle and diffuser make things go fast or make them go slower. The rest of this, they don't really speed them up or slow them down. Inside, they might a little bit, but not overall from inlet to outlet. How about the change in enthalpy for a throttling device? How's H2 minus H1? How's it compare? It's what? Throttling devices are isenthalpic. 0. This is a conceptual thing. A lot of people will say, hey, you have no heat transfer, it must be isothermal. Wrong, right? Pressure goes down, temperature goes down, and boom, you have it's like ready for refrigeration. It's ready to cool something. And it's isenthalpic, constant enthalpy. All right. With that, I'll go ahead and stop. Thank you for your attention.